Good morning. It's day 3 of ICAS 13. I'm so glad to see you today here at the Global Convention Plaza. So just like 2 previous days, I'm going to give you a quick orientation about today's program. Yesterday, actually, we had a beautiful night at Sevisum for conference banquet. We had a nice music, Korean music, and beautiful scenery and food and all good people. So I truly thank everybody who came for this conference banquet, and especially those who made this possible, all the staff members and students actually who served behind the curtain. Thank you very much to everybody. And by the way, the photo on the right-hand side is the photo I took with my cell phone. But you are going to have much better photos on our Flickr site made by the professionals today. Okay. All right. So talking about photos, actually you might have already visited this Flickr website, Flickr Photos ICAS 13, and there are many albums for each of the sessions and the tour programs. So actually they keep uploading these photos during this program today. So actually please check and then download your photos and share with your friends. All right, so yesterday the weather was so beautiful, so actually we were able to show what we wanted to show during this campus guided tour. So these 2 students of Seoul National University actually did a fantastic job for this campus guided tour. So actually today you have a last chance to enjoy this walking tour. So if you want to join, please come down to the first floor after a quick lunch. Actually they are going to leave at 12:40. So hope you are not going to miss this good chance to walk around the campus and hear about the history and the vision of the Seoul National University. Okay, and then I really want to have a strong finish of this conference, so please stay until our closing ceremony at 5 o'clock in this auditorium. First of all, actually, we were not able to give these student awards to these 3 students because of the miscommunication, so I sincerely apologize for that. So please help me make up for it. So please come to this award ceremony, and we are going to give the certificates and prize to these 3 excellent students. And then organizers of this next ICOSAR conference will make a presentation to invite you to Shanghai. So actually when we had the previous ICOSAR in Vienna, actually they allowed me to talk about this ICAS. So we are going to help each other in this way. So please come to this closing ceremony to hear about what you are going to enjoy in Shanghai in 2021. And after that, organizers of ICAS 14 will talk about their ICAS conference in Dublin, Ireland. So actually, we look forward to seeing you all in Dublin, and we are going to have this presentation today. And then actually, the deadline of your self-nomination for awards for active participation is 3:30 today. So please share your nice photos by sending email to icas2019@gmail.com, or just put the hashtag ICAS13 on your Instagram, and then use a networking feature of your app so that we can share all the good photos. And we are going to give nice prizes like a Galaxy Tab, AirPod, and the beam projector to those who are in this room only. Okay. All right. So I look forward to this event this afternoon. Finally, we have a couple of tour programs, and today we are going to have a Seoul City tour. By the way, the Seoul tickets are all sold out, so please do not ask me about the additional tickets. As a chair, there are some things I cannot do. All right. So these buses will leave at 5:30 after this closing ceremony at this first floor of this building. And then post-conference tour tomorrow, actually there are some boarding times and locations, so please check the bus number on your badge to take these buses. Hope you are going to have a great time through these tour programs. All right, and finally, after today's keynote lecture, we will try to have a group photo for everybody in this building. So After Dan gives his trophy to the Leonardo, please come forward and take one big group photo today. So I really look forward to it. Right. So it's my great honor and pleasure to introduce Professor Dan Francopo from Lehigh University. He's going to chair today's keynote session.
Thank you.
Thank you, Dan.
Thank you.
It's also my great honor and pleasure to introduce the keynote speaker, Leonardo. Leonardo is well known in our community. He is from Columbia originally, and he graduated from MIT in 2001 with a master's degree. In 2005 from Georgia Tech. In 2006 he joined Rice University, which is now an associate professor there. And after he developed computation and analytical methods for performance assessment and resilience of infrastructure and structures, and looking at interdependence. He's very well known in our community and is a research not only in civil engineering but also in other fields. Leonardo got also recognitions for his work with at least 3 very important awards. He got the NSF Career Award in 2008. He got also EIRI award for a paper, and in 2017 he got the ISR Early Achievement Award, and I had the pleasure to give him this award in 2017. Today he will talk about computer reliability and resilience verification for infrastructure networks. So Leonardo.
Thank you, Dan, for the kind introduction, and thank you, Junho, for inviting me to be one of the keynote speakers of the conference. And thank you, all of you, for being here. I know that after a wonderful banquet, wine and food, this commitment of the ICAS community to be early this morning. So my plan is to introduce a couple of methodologies that I feel could be interesting for our community to study complex engineered networks, and in a way that we can guarantee the quality of the estimates that we are trying to establish. So before getting into all that, let me just remind us that scientific computing in our community has had already a great impact in major endeavors in our progress, spaceflight, energy. By the way, this is me in Chile after the 2010 earthquake in an ultra-high voltage substation. And scientific computing has helped us analyzing great events, and hand in hand with physics-based understanding, we have been able to make this progress. The challenge that we see as we move forward is that the systems are becoming more complex than this. They are already complex, but there are some added layers of complexity, and a couple of examples of the systems that we see already are like smart cities or autonomous habitats. Characteristic of these systems is that they are almost paradoxical. They have a lot of autonomy, but yet they have a lot of human-in-the-loop influence. They have a lot of interdependencies, and yet they can also operate in an almost decentralized fashion. They obviously are governed by physics, but physics is no longer the main ruler. There are these other effects that can wreak havoc on these systems, the human-in-the-loop, the automation. And yet we are also the engineers who had to certify the safety and reliability of these upcoming systems. So we have that challenge, and we need to upscale the techniques that we have so that we can guarantee or certify or verify the estimates of what we compute. So let me continue here as an example of a system that we have had for 100 years and exhibits already, or has exhibited already, a lot of the hallmark features of complex engineered systems. The power grid. Empirical data from outages in the US show heavy tails on the outages, and this one is just an example of a test electrical power network used in the community, the IEEE 118 node network. Some of you use it. If you analyze this with all the dynamic power flow, you see the power loss, in this case a ratio of power shed versus power demand. I'm highlighting the power loss because power loss are a feature of complexity, a feature of complex systems. in loose terms, you don't have a typical behavior. You have a very long tail, and those are hard to handle. What we call rare events, in these tails, they are rare, but they are more likely than many assumptions we sometimes make that our systems have exponential decay tails in the probabilistic space. So, just as a wake-up call here, if we want to estimate a property of one complex system, what we typically do is we just sample random variable or realizations of the random variable, and we somehow compute an estimate of that. But how many samples do we get? The stopping rule is a key feature of what we are going to try to address today. So I'm not going to ask, but if I were in class, I would be asking first student here. Well, the stopping rule in general, if we ask it, people will say, well, we do it until we see that the estimate starts stabilizing, or some measure of coefficient of variation, let's say, also gets small enough. But that's almost eyeballing. So that's important for understanding, but it's not really to certify a system that is perhaps autonomous in the future and that can impact data. So a more desirable stopping rule is something like guaranteeing that our result is with very small probability exceeding an error. Here it is, small probability exceeding an error. These are parameters that we define according to our acceptance of risk. And therefore, the stopping rule, how many times do we perform our experiments or run our simulations, is going to depend on that. Most of us have relied on the central limit theorem and laws of large numbers to perhaps establish what the stopping rule is. But I just showed you the previous slide. The complex engineered systems, and they are becoming more complex, they sort of violate some of the premises embedded in establishing stopping rules on the central limit theory. Because we have finite number of samples. We don't even know the shape of the probability distribution that we are trying to estimate. So just to show you an example of how we can violate this, I think the urgency of us looking more closely. Here I have a Pareto distribution, and here is the epsilon. Remember, epsilon is the error in our estimate. Delta is the probability that we are accepting certain error. So it's a grid there of values, they go, and red is bad. Red means that even though we have used the number of simulations established by the stopping rule of a central limit theorem-driven analysis, we are violating it. We are violating the probabilities because Pareto is heavy tail and the assumptions of the stopping rule are inconsistent with it. Complex systems tend to exceed that power law. Not only in engineering, but complex systems in general. So let me just highlight a few of the features of our engineered systems that add to the already increasing complexity. One of them is that they are large scale. It's hard to keep them bounded. They are very heterogeneous because of the aging and deterioration, heterogeneous in the probabilities of failure of components, heterogeneous in the types of components, and the two things I mentioned before, interdependencies and human in the loop plus automation. So again, we still have the responsibility to certify safety and reliability. We are the reliability engineers. And what do? The first thing I hope we can try to do is understand the limitations on the tools that we have and see what others who have faced these challenges have done as well. Don't forget our history, not only in our field, but other communities. So let's move forward here. One of the things is looking at the state space of these systems. If we want to certify something for complex systems, it's a good idea to understand the space of configurations of the system, how the system will live. And we have that reliability lives in a space, in a power set, space 2 to the n. If you have n components in your complex system, the space of configuration is 2 to the n. It grows exponentially. If you think of resilience, it's an even larger space, a permutation space, n factorial for large n. And those large spaces where we're going to embed ourselves in, obviously are so large that we need some clever ways to get into them. What has been done before in this type of problems? From the logicians and computer scientists, there have been some progress for the problems that are reducible, or reliability could be reduced into a Boolean satisfiability problem. computer scientists have dealt with satisfiability. Satisfiability is essentially you have a bunch of variables, Boolean variables. They can be true or false, and you have logical statements linking the variables. It could be logical or, logical and, implications. And you want to evaluate the truth of the whole sentence or formula. So satisfiability solvers exist at the industrial level, and they solve millions of variables as of today, even though the problem is NP hard. Why? There's a lot of understanding about the complexities of that particular problem. For resilience, well-known problem is the traveling salesman problem. It could be reduced into resilience, and it's also very hard, and yet solvers in practice, one of them is a solver in Georgia Tech where I graduated, it's called Concord. They were solving up to hundreds of thousands of variables. So that's progress, and I think we can get inspiration from that and borrow some ideas, because systems in our community, if we get in the hundreds of elements for a network, we're already unable to certify guarantees on our estimates. We are almost doing it naively, not entirely, but the scalability is perhaps 100,000, but not hundreds of thousands or millions. So, I'm going to try to address some of the techniques that might be promising to solve that challenge. But before, I will start with a very brief sort of context of the landscape of techniques in our community. And this is my interpretation based on my own biases and studies, but I think it helps as an organizing principle. So I'll start with that. The sections 2, 3, and 4 are the core of the talk, the new methods. One is sampling-based, probably approximately correct strategies. We'll get to that. Another one is dispensing sampling and doing exact counting or counting without having to rely on randomization. And the other one is exploiting perhaps the emerging promise of quantum information processing. So let's start with the first part, our landscape. So I'm going to show a reliability tree, literally. Okay, that was my way of trying to make you laugh, but it didn't work out. So this is a tree in which I will put some techniques. The first branch there is the branch in which I put what I believe are the Monte Carlo simulation strategies, and the acronyms are there. We see important sampling techniques, techniques based on design of experiments like adding hypercube and the like. Optimal Monte Carlo is also there. Optimal Monte Carlo is a Monte Carlo strategy that gives us a stopping rule that guarantees results without any assumptions. And I put it there as the gold standard for that branch. And also generalized splitting. I'm going to elaborate briefly and give you the intuition of generalized splitting, because I realize it's not necessarily widespread, but we have seen it before, just in another disguised way, I think. The intuition for generalized splitting techniques is that if we want to estimate rare event probabilities, they could be the larger ones. And we can establish a multi-level sampling where we sample larger space and we keep reducing. Once you have all that, you tally things up and you get a very good estimate for rare event estimation. So 3 things I will say here. Some of you might be itching and saying this looks like subset simulation. It does look like subset simulation because it relies on the same principles. However, it's different in the following sense. First, generalized splitting is more efficient, scales log 1 over p. The regular one is 1 over p. Second, this generalized splitting is able to provide unbiased estimates, and it also certifies a property that is still desirable. It's not an error and delta certificate, but it does verify the bounded relative error. What it says is that the more you sample, your relative error is going to tend to a constant. So that's still desirable. But these are, in general, the lineage of all these are guarantee-less. They cannot guarantee the error with a small probability. But progress is being made. Now let's take the analytical branch. That's the one I hang on most of the time, and it has a lot more techniques. Starting with techniques that are purely exact, like the PDDs and recursive decomposition algorithms, and some of the Bayesian networks, and we have colleagues here working on that. Our host has been working on the RDA, and Daniel and Iris have been working on the PDDs and Bayesian networks. And I also put in this branch techniques that led themselves to analytical or to analysis. Even if you use a surrogate model to enable those analyses, but you have more control of the problem and still issue results with greater sense of understanding. And those are like the polynomial case expansion, and you can ask Bruno for that, or the probability density evolution method here. We have the group from Tongi working on that. I will give you the intuition for an exact technique, just as a matter of context, and since our host is here, it's going to be the technique based on selective recursive decomposition algorithms, or in a more general sense, state space partition models. And the intuition is as follows. This is a very small network, 3 elements. Without doing anything, you just don't know if the elements are there or not, and the idea is to partition the state of that network into subspaces, and the subspaces will exactly partition into failed subspaces and safe subspaces. And in this little figure in the left, what you have is simply one network, but you have it in a space, in a hyperspace of 3 dimensions. You don't know what is going on. But if you take the very first one, you know that the first 2 elements are, let's say, failed. Since you know that those are failed, it doesn't matter this remaining element what it takes. If it is failed or not, you already know that the whole thing is failed. So the state space partition exploit that. You know that something is happening, and then regardless of what else is in your surroundings, you need to explore that. Similarly, for the safe side, you have 2 elements that are safe, and here I'm implying connectivity, all terminal connectivity as a goal. Here you have 2 elements safe, you already satisfy the requirement of all terminal reliability. So you don't need to have any exploration of the remaining elements. So for large networks, you explore sets, and you get away by not needing to explore the obvious ones. And but problem is that that doesn't scale too much. So let's go to a branch, the one I will be focusing mostly today. This branch is the probably approximately correct branch. It sort of takes the best from the 2 previous branches. It does some sampling, but it also does some exact and tries to combine the things together. 2 of the major examples in this category that are relevant in our community is the Karger graph theoretic algorithm, and the intuition is underlined here. When you have a graph, the minimum cuts are a polynomial number of them. Therefore, you can count them or you can estimate them. The minimum cuts that matter. You can disregard some of the minimum cuts that include too many elements because they don't contribute much to the probability. Accepting that, there is a theorem, and then we can verify with this epsilon delta guarantees your results. In fact, I mentioned this one because this is the first fully polynomial randomized approximation scheme. What it means is that it's efficient and it gives estimates that verify error and confidence. And to the right is our own proposal called RelNet. It relies on the strategies of hashing and counting. We also verify the error. This is a multiplicative error, which is a little bit more decidable in the rate event estimation, because we are doing relative to the estimate, as opposed to an absolute error. When we are in 10 to the minus 9, minus 10, absolute errors might start losing the power of discerning what you are dealing with. But relative error will always be telling you how bad you are. So we are able to verify that one. And the basic intuition of it is, we again go back to that combinatorial space. And we try to partition that space into uniform subsets, find at random one of the subsets, count exactly the configurations that satisfy our requirements like reliability, and then multiply backward. Doing all that, we are able to guarantee the errors and confidences that we propose. So let me get a little bit more in detail on that, to make sure that we gain some understanding of the principles there. So this is a very simple network there, really simple network, 2 nodes and a directed link. You have variables that describe the links of the network in a set X. I'm going to be expanding this for more general. And you have variables that are auxiliary variables that are related to the nodes. So let me write first a logical statement. I've talked about Boolean logic and Boolean satisfiability. This equation in blue is a Boolean formula. is saying that a variable conjuncted with another variable, the conjunction is the logical AND, could imply another variable. What you do is you check if each of the variables is true or false, and you compare it against the truth table. This is the foundations of set theory and mathematics. So this is, you satisfy that is satisfied. An example to show that satisfaction that is relatively intuitive is if I have the node, the variable associated with the first node, if it is true, and if I have the variable associated with the link that is true, then I can logically imply that the end node is also true. In the canonical form of reliability, network reliability, where the edges are the ones that are stochastic. If the nodes are stochastic, it can be reduced into only edges stochastic. But that formula is there because when we start thinking then at a more global level, we need to put many of these things together, stitch them together. And it's easier also to look at unreliability for the following reason. If I am a node in a 1 million node network, and if I know that I'm disconnected, I know that the all terminal reliability for the million node network is also disconnected. So I have a lot of information power. And therefore we're going to go and verify unreliability. So the formula is going to be looking like this. It's at the bottom. I have the same implication, and I have a few other terms related to the start and end. For every network, we will have a set that we want to have connected. And the formula can be reduced into what is called a conjunctive normal form, which is a disjunction of conjunctions or ANDs of ORs. We take those formulas and we feed them into these industrial level SAT solvers. The ones that take million variables, they can solve this and find a solution. So we are treating the SAT solvers almost as an oracle. We can ask a question, a difficult question, the oracle will give us the answer. Because they have the power of handling this large scale. Now, the only caveat is that our formula is bracketed in an existential quantifier. The importance of having an existential quantifier is that reliability is hard. And we cannot say for sure with just the expressive power of Boolean logic. So the existential, what it says is, there exists a set that satisfies what you want to evaluate. That there exists is kind of a wishy-washy, but if the SAT solver gives me a solution, a property of NP-hard problems is that you can check the solutions very easily. If I offer you a solution, or the oracle gives me a solution, I can check if it indeed is one or not. So checking is easy, and that's kind of where the strategy is. So let me go for, this is just another example, we'll not explain it. This is another network, just to see how the formula will grow. If the network keeps growing, the formula can still be written, it doesn't grow exponentially, but it becomes more complicated. SAT solver will help. Again, the intuition is, we go into the space of configurations. So we're looking at where the system lives. We do the hashing. Hashing is the technique that allows us to basically do a dimension reduction. We go from 2 to the n to 2 to the, in this case, hm, or we go from a space of 2 to the n to a smaller space, where the smaller space is the number of cells that we need. And then we get enough cells so that we can count inside one of the cells, and then we amplify the results. Some results. If we have a network here, a grid, grids are very good, idealized testing beds, and if we want the K-terminal reliability, where we want to have connected the checkerboard pattern there, every other node, we want to ensure that they are connected. When every node is every link is stochastic, sorry, and the probability of the links is changing. Oops, sorry. Probability of the links is evaluated for various levels: 1/2, 1/8, 1/32. And we see that the scaling in time is exponential. The problem remains exponential. It's always. But what I want to highlight is that our empirical error remains very small. For this, we established let's not exceed a 20% relative error. We never exceed even 10%, and with very high probability or confidence, 1 minus this delta. We apply that also to realistic networks. We have a set of about 58 power transmission grids in the US. This is a subset of the 20 of them, which range in sizes of 60 to hundreds of elements. Here are some of the topologies: Dallas, San Antonio, Austin. And you see that with that RelNet, that hashing counting technique, we are able to, and in this case we have had that 20% error. We do the simulations, we stay within the bounds. Now you see some of them exceed, because we allow for a small probability of exceeding the error. So we certify the error and the delta in this way. But it had to have all these components of the Boolean, hashing, and count. The one is there, now we can really take it as a variety of problems and doing the translation. So I see I'm looking at the clock here, so let me go into another strategy. Sampling, as we saw, the technique grows exponentially. So eventually, if I feed a very large network, it's going to falter. So why not dispensing with sampling? Can we do anything without sampling? Since we started to gain insight of the space of configurations, why not immersing ourselves into that space more? So the strategy is intuitively simple. 2 to the n is the space that we live now, and reliability is a subspace there that we know now we can calculate with this satisfiability approach, with this extension formula. But it's complicated if we try to do it for rate of n. So why not solving another problem? In this case, an edge-covered problem. I'll explain what the edge-covered problem is. But it's a problem that entirely contains the all-terminal reliability. And just by looking at the complexity of the formula, it seems easier. Because edge cover happens to be a locally minded problem, whereas reliability or unreliability is a global one. So local problems are always good because they scale very well. So RelNet, this just to show you a configuration for a small network. So again, reliability requires some global satisfaction. The edge cover relaxation for this could be like this one. Edge cover means that you need to have enough edges such that there is no isolated node. So you have more configurations that satisfy that than configurations that satisfy an all-terminal reliability. But once you find this one, you can go and verify if it satisfies the reliability or not. Or you can modify this one. It's a very good starting point and try to find the ones that you care. And the formula can be read. But when the networks scale, we run into a problem. If we don't do sampling, before I fall off here, sorry, walking forward. Sampling doesn't have, let's say, memory issues in general. But here, since we are not sampling, we need to keep track of our space. So the issue is now space, memory. So what techniques allows us to do memory efficient computations? Well, it seems people in linear algebra have hundreds of years at developing strategies to handle information. So tensor networks are a very promising strategy. A tensor, you might very well know, a 0 rank tensor is a scalar, 1 rank tensor is a vector, 2 rank tensor is a matrix, and so on. If you have two rank tensors or two matrices in our parlance, and if you connect them, you can contract them. You contract the shared index, and that will give you basically another matrix. The operation is spelled out here for this little example. Or if you have two matrices, two vectors, and you contract the shared index, what you get is a scalar. So you get a number. Or you can have more complex networks, and if you do the tensor contraction, in the end, you end up with a number. And that number could be something that is useful to you, depending on what the tensors are. So if the nodes happen to be tensors that encode the logical OR, the truth table of the logical OR, which is satisfied for every combination of the two elements when at least one of them is satisfied. So you encode that, and if every node has a OR gate encoded in it, and the links have also an encoding such that they are existing, then you can do the tensor contraction and you get a number in the end, and that number is the number of configurations that satisfy the edge code. How that happens, that's part of the design of the algorithm process. If you use other logic gates, you might get to solve other problems. And this is memory efficient because instead of dealing with a rank n tensor, you're just dealing with a bunch of small rank tensors. For our application, the rank is typically proportional to the degree of the nodes. Those are relatively small in our method. So it scales so well. Let me show you some results. This is for grids where the parameter n here is a side of the grid. So we have grids up to 10 by 10 or 100 elements. And we are counting edge covers. Our attempt with the tensor network approach is the black dots. And these I coded in my laptop with MATLAB, so not even trying, and it did scale much better than other established techniques, like the binary decision diagram, which is exact, or ApproxMC is the equivalent of RelNet, but for these edge covers, so it's that hashing, counting. Just to have a comparison, it's this red line. And then optimal Monte Carlo is also there. Optimal Monte Carlo is the one that guarantees results, but it's something based. So this really starts that maybe looking at the problem at an entirely different angle, like an algebraic one, will have benefits. In terms of the results, here are the benefits already. Our results are the black dots again here. The gray shading is the anytime bounds from a recursive decomposition algorithm. The algorithm doesn't scale well, so the bounds just start getting almost like 0, 1. So this approach breaks through those bounds, so you get a better bound already there. Binary decision diagrams are naive, they don't scale. And just for comparison, I have here the actual reliability computation. And so this is edge cover at the top, reliability computation at the bottom. Comparing the two, the biases could be maybe exploited and use one for the prediction of the other. But more importantly, remember that our problems have long tails and rare events don't necessarily have sort of a typical failure mode. So it might be the case that tails exceeding from this estimation can find a hard bound there from the other problem that we are able to complete. So there is many on this, but we still need to tighten this up. But the algebraic methods do offer that advantage both in memory and efficiency if there is an ordering of the tensor contraction. So putting all this together, it turns out that putting it all together, I mean the Boolean view of the network reliability problem plus the tensor view of network reliability problem. You put them together and it happens that physicists have been looking at similar things for quantum many-body systems. When they look at particles at the fundamental level, they behave in a very complicated manner. And they have figured out that tensor networks were a good tool to describe things. And what they didn't have was the satisfiability side. So we're trying now to combine those things in another way. So before I get into the developments, let's just have the basics of quantum mechanics here. First, a classical bit, 0, 1, at any time. A quantum bit, before you measure it, it is consistent with having a superposition of, let's say, up or down, or a single bit. It is consistent. How do we know? Because if you go and measure and do monitoring of the qubit, you see that the results are consistent with it having been in any superposition state. So that's interesting, but that has been also, there is a famous experiment from almost 100 years ago, the double slit experiment. It verifies that superposition. There are a few other properties that are unique. Entanglement, which is a form of almost supercorrelation. If one qubit is doing one thing at the moment of observation, another one that has been entangled will be entirely correlated with the prediction. And there is another property, interference. Interference. What happens is that this, the qubit, you see this notation here, the 0, 1, and that is called the Dirac notation. The states are typically representing a Hilbert space. Hilbert spaces are the ones that embed the energy of systems. Any system has energy, and the energy is described as a Hamiltonian. So Hilbert space embraces the Hamiltonians. But what I was going to say is that the vectors in a Hilbert space could have complex number amplitudes. You can decompose a vector into its bases, to orthonormal bases, and the multipliers of each of the bases could be a complex number. And if it is a complex number, you can actually destructively interfere, so you can suppress state that you don't like, and you can amplify state that you like, much like waves. Some waves interfere constructively, some destructively. And you do that such that when you do the measurement, what happens with a quantum system when you do the measurement, whatever superposition you have collapses into a single state, but it will be a state that is proportional to the probability of the probability informed by its complex amplitudes at the moment. So if you fiddle such that you amplify what you want, you will get the answer that you need. So it's almost like a coding level. Two more things that are unique to the quantum systems that are unusual. Here to the left, the simple inclusive OR that I have described for Boolean satisfiability. That's the truth table actually. If false, 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 if false, true, true, and everything is true. In a quantum system, the fundamentals of quantum logic are not satisfied with these kind of tables because the inclusive OR is not symmetric. The order in which the operation takes place will alter subsequent results. Measuring quantum systems disrupts them and changes them. So there is a need for precedence here. So since I mentioned measurement is a very sensitive thing. Whenever you have a quantum state, either a quantum bit or many quantum bits together, could be a superposition of them. The moment you do a measurement, collapses into a single bit. So we need to take advantage of the quantumness before the measurement so that we do with those interferences and entanglements and all that. But what you can measure, nature has restrictions. It's not that we can measure everything we want. The measurements are only things that nature allows us to observe, and they happen to be encoding the Hamiltonians. Again, Hamiltonians in physics is what describes the energy of any system. So if you have a Hamiltonian, and if you represent it as a matrix, the eigenvalues of the Hamiltonian are the energy levels of your system, and those are the only things that the measurement will reveal to you. So a measurement is not that we want to go and measure what we want. It's what nature decides to let us know, and it's only energy levels that are quantized or other things that you decide. So it's very particular. So designing an algorithm to exploit quantumness, even though it's very powerful, we have so many restrictions. Not to mention restrictions then in the physical realization of the quantum system so that you can perform the operations. Or coding an algorithm in a language that will understand the quantum mechanical logic. So this is an example of some early efforts now of codes. This is a simple code where you have the lines are represent qubits, and then you have 2 qubits, and the H is so-called quantum Hadamard gate. What that gate does is if you feed a qubit with a state 0, the Hadamard gate goes and creates a uniform superposition of 0 and 1. It's a logical operation that takes one thing and makes the superposition equally likely of the possibilities. And then this is a control node to realize a formula, to realize or to measure something that we care in engineering like reliability. We need to be at the level of these logic gates, and that's why expressing our problems in the language of the Boolean satisfiability is the currency that we needed, because it's already at that gate level expressiveness that it could be coded here, and the circuits could get deep, and that's a problem as well, because the circuits of today are noisy, and I'll get to that in a second. But we have some ways of coding. We understand the possible advantages. So now the hardware. This is another challenge that we have. IBM has been leading the pack on quantum hardware. This is the chip of the IBM quantum experience. This is a picture of a 5-qubit chip whose internal logic is connected in a star shape. They take advantage of the quantumness because they are super cold qubits or elementary particles, electrons in particular. This is a cooler, and the chip is hanging at the very bottom. You need to have as cool as possible because interference or vibration of particles is tantamount to a measurement. A measurement doesn't need to be an apparatus that goes and measures. Just other particle neighboring your system will effectively measure it and make the wave function collapse. So you need to be ultra cold because at the ultra cold temperatures, things are quiet. Now let me make a remark here. This is an interesting coincidence. These ultra cold quantum bits and they are entangled via wavelengths and the like, they rely on Bose-Einstein condensates. And yesterday we were celebrating the C. Allen Cornell Award. Cornell's son developed the first physically realizable Bose condensate, and he was awarded Nobel Prize in 2001, if I'm not mistaken. So our community, by extension, has had tremendous impact on all this at the fundamentals of uncertainty. I thought that was an interesting connection. So I allowed 1 minute to express it. So let's move on. There is NIST-like hardware. I have many colleagues here working with NIST in the engineering division, but the physics division has been doing ion traps. So they don't do these sort of artificial atoms as IBM and Google, Intel, every other company are doing the superconducting. NIST is doing physical atoms, physical charged particles, and they are trapped with electromagnets and cooled down with lasers and manipulated with optical devices. Is a complexity of unimaginable magnitude, and they have succeeded. And the advantage of their approach is that the qubits are fully entangled, they are interconnected, all with all. That is desirable, but it's much harder to control, to scale. So research viability to some extent. Now there is another quantum hardware out there. You might have heard about the D-Wave hardware. It's a Canadian company. We have Canadian colleagues around here. D-Wave is weird. It's on the thousands of qubits now. The other ones are in the tens of qubits or maybe up to 100. D-Wave is in thousands. They just announced last month the Pegasus chip with 5,000 qubits. So these are qubits that are noisier and they cannot be programmed with the quantum logic. You cannot write a program. What you do with this D-Wave, that's why it's sort of a separate category. D-Wave is now referred to as a quantum annealer. You translate your problem into a Hamiltonian, going back to energy. And nature, the only mission in nature is every system has to spend the less energy or be in the lowest state energy or the ground state. So what it does is you encode your problem into fundamental particles here, or properties, spins of electrons or the like, and you prepare them in a configuration that is easy to prepare, and the Hamiltonian will guide the system towards its ground state. When you get to the ground state, that would be tantamount to having found a solution. So a quantum annealer. What is the secret sauce there? Well, what happens is exploit the physics of nature. So if you start, let's say, with 2 qubits here in state 0, 0, you are stuck. For you to get to a best answer, you need to go up and down classically. Classically, you need thermal expansions, or we even use in simulation, we call it simulated annealing. Well, in the quantum realm, if you are here, because the wave function is a wave, there is a chance that you tunnel through and get into the lower state, because nature allows it. So that's what it does. It slowly but surely evolves your energy to lower and lower levels by tunneling through energy barriers. So, having said that, it seems we have the ingredients. We have logic, we have possibly hardware, and we have encodings of engineering problems into a language that is readable by the quantum algorithms. So here we have the, let's say, a 4-node network. This is the Boolean formula, remember, with the first terms looking at the ST or the source and terminal, or you have it, and then the other terms are those implications. Well, we found a mapping of that into a Hamiltonian. So that was working with physicists and feeling the thing. The Hamiltonian is here. It is a product of fundamental so-called gates. These are poly gates or poly matrices. What matters here is that we can translate more easily a Boolean statement into a Hamiltonian that encodes what we want for the edge code. So we have that mapping, and then we run it. What do we get? Here I'm showing for a 4-node network. Let me start in the top left. The quantum annealing, what it does is you prepare the quantum bits in an easy way to prepare. You put a magnet and they are all spins up, something like that. So it's easy to prepare. Initial state, you are here, and then you slowly nudge it towards your desired Hamiltonian, which is the one that encodes the solution. That is the quantum adiabatic evolution. And there is a theorem it used to. If you evolve it slow enough, you will be guaranteed to find your solution. Now, slow enough is initial to be resolved, but here what I'm showing is that you do that nudging by just linear interpolation of reducing the strength of the initial configuration and amplifying the state of the desirable configurations. And at every instant in time, you're solving the Schrodinger equation. This always brings me back to the PDEM because you are evolving a probability. So there might be some connections there that are not found yet. And here, this plot at the bottom, what it shows is that for this very small system, we know the answers ahead of time. So what we put in the lines is the solutions. And then the solid lines are the Schrodinger equation evolving. And then we measure, it collapses, and it tells me the probability at every instant of time of being in that ground state. If I do the evolution slow enough, I pretty much, with 100% probability, find the solutions. So banking on that, we run it for a larger network, up to 25 qubits. And our results implementing the algorithm are here in blue. This is a quantum alternating operator approach, which what it does is quantum annealing, but also, this is the engineering side of things. It does the quantum annealing physics, but then we get a result from that, and we do classical optimization to drive further the finding of solutions. And then we feed that back into the annealer, and you do that for a number of times. So this is the so-called QAOA algorithm. This is what is as of 2019. Last year, this was not yet the most promising approach, so things are moving fast. But we get good results. So this is with the annealing, alternating, and the red one is the optimal Monte Carlo. So it's a Monte Carlo that will guarantee results. And we see both are scaling exponentially, but we see some improvement there. So there is a lot of hope for things to work out. So let me go further here. Going back to our tensor networks and putting more things together. If you have qubits in a network and the qubits are assigned to the links, at some point you can have a state of the network that is a superposition of all possibilities. That's a valid state internally. But you need to actually measure something. So what we realize is that the Hamiltonian of this network, we can construct it, and the eigenvalues of that network, or that matrix, the eigenvalues that are 0, and all these degenerates correspond to the solutions of the problem. For the edge cover problem, not for the reliability, but for the edge cover. We don't have a Hamiltonian for the reliability yet, but these are the things. Algorithms are being kind of developed on the fly, trying to exploit properties and discovering what could be useful from them. So this could be useful for counting because the quantum annealing gives you only one answer every time you measure. This approach with the quantum tensor networks would give you a number of things, as opposed to a answer it will give you the total number of answers that satisfy your constraints. It's something better than, and more relevant for reliability. So trying to wrap things up here, it seems we have another tree, the quantum tree, and we have the quantum tensor networks, the QAOA heuristics, and what I envision in the future is the quantum annealing with the PAC guarantees. So if we put them together, at least in my view, there is promise in the PAC world, classical and quantum, but both are really standing on very strong trunks here from other techniques, because the weaknesses or strengths of other techniques are the ones that inform what could be tried in this kind of Wild West realm of the quantum algorithms now. So, just one last slide here on some Outlook applications. Obviously, we are interested in larger networks and interdependent networks. The encoding, it seems that the Hamiltonians, they are just gentle objects. We just need to know how to encode things, how to square the circle. But hierarchical representations are also natural for quantum systems. You can actually coarse-grain things via these entanglements. So there might be a promise for doing hierarchical modeling. Multi-fidelity abstractions as well. You can have coarse graining of the system, but to guarantee the results, you can maintain a core part of the network still at high fidelity so that your assessments still are tied to some established accuracy or performance. And we got inspiration from the computer scientists on these satisfiability problems and the traveling salesman problem and the like. It seems now there is interest from what we have developed feeding back into other fields like automated systems or autonomous systems. NASA is there in Houston, so we have had the chance to see that there is a lot of interest in encoding constraints for automated systems like distance to the left foot and angle of the arm. And for these things, they are going to live in a combinatorial space, and if you want to certify the reliability of the actions, you cannot sort of leave it to sampling alone, because you might be getting multi-million-dollar probes there stuck. But if you do a sampling that guarantees ahead of time, then your decision has been more informed and the risk has been at least taken into consideration more fully. So I think with that, just 3 points I want to highlight before we move on to the Q&A. That the probably approximately correct, I believe, could be a good framework to embrace for certifying error and confidence. We also see that methods beyond sampling should be tried. We need to understand our enemy. That's how people from the satisfiability and the traveling salesman program have made progress. Not just from the initial strategies, but by getting deeper into the structure of the solution space. It's an overwhelming solution space, but any fraction of understanding you get there scales out very quickly because those spaces are exponential. And as a last thing, it seems there is promise with these quantum devices. All the technology as of 2019 is now grouped into the so-called noisy intermediate scale quantum devices. Noisy because there are a lot of errors in the gates. Those quantum logic gates, they have errors up to 3 in 1,000, and those accumulate if you have deep circuits. There are errors measuring. They are 2 per 1,000, so there is a lot of error correction still needed. But still with those that are available, I think it's safe to try algorithms. Algorithms are sort of hardware independent for now if we write them in the language of the Boolean logic. So with that, thank you very much for your attention, and I think we'll open it for questions.
Thank you, Leonardo, for this captivating lecture. So I am sure we have questions, and the floor is open to these questions. So I am sure there are questions, but now
Yes.
I'm not sure. But we have one here, yes.
Eventually, at one point, you have to solve the Schrödinger equation, right? And the major limitation in quantum computing is to solve the multi-body Schrödinger equation. That's actually, so where is the gain here?
Yeah, so here we are simulating, and that's why we are doing up to 25 qubits, because it can be done up to that size. Now, getting confidence by solving this simulated Schrödinger equation, then we can actually go full into the hardware. If I have gained confidence into my Hamiltonian coding, I can go into the D-wave, feed a very large system, and I will have an answer that I might be more likely to believe. But yeah, scalability remains an issue. However, if we establish this pack quantum, we can get maybe results that give us that error of confidence for the quantum systems. So I hope that addresses. But yeah, as of now, the simulation, in fact, there is a need for simulators and emulators of the Schrödinger equation, because we need to compare against something, and there is no gold standard that scales out.
Thank you.
Other questions? Please.
I think the concept of quantum is a very frontier concept, and for engineering whose experience in the quantum is really sparse. And how do you think how many years it takes for it become popular for the quantum, for algorithm you proposed.
So I think with this noisy intermediate scale quantum devices, basically the technology we have today with Google, Intel, IBM, it seems now more plausible than ever than within the next decade we certainly will see some scaling. It's not that we are going to be solving the exponential scaling problem, but we're going to be expanding the range and complexity of the problem we have today. To me, if we go for neighbors that we cannot solve yet in the thousands, and we are able to achieve that, that is already a big improvement. For a computer scientist, that might not be their goal, or for other scientists. But 10 years into it now, this answer is so hard. Everyone has been predicting this since Feynman was talking about quantum computing. But there is a turning point, and you might see it in those companies all investing. Also in the research programs from our funding agencies. In the US, the NSF has one of the 10 priorities of this decade is quantum information. It's listed in the grand challenges. Europe has invested quite a lot. Canada, Australia has a big program. So it seems there is more of that. Now, it might fizzle out. If it fizzles out, we are still gaining because we have all these algebraic formulations that were not necessarily part of our repertoire to solve the problems. And I think we just gain insights anyways. But
Okay, thank you.
Other questions? If not, we have to close here, and thank you again very, very much for this wonderful lecture. Thank you.